Welcome, ladies and gents, to another flipped lesson. Today we're going to be focused on reactions and equations and how to balance chemical reactions. This is covered in pages 282 to 288 in your text. Our main idea for today's lesson is chemical reactions are represented by balanced chemical equations. So a chemical reaction, as we learned previously, is the process by which atoms of one or more substances are rearranged to form a different substance. So a quick review of signs that mean a chemical change has occurred is if you have a change in temperature, a release of energy in the form of heat or light, a color change, odor or gas bubbles produced, or formation of a solid. Any of these two or more things together typically tell us that we have a chemical reaction taking place. So what we use to represent chemical reactions are chemical equations. They're separated by an arrow, and what that arrow does for us is it puts the reactants on the left and the products on the right. So the reactants are the pieces that you put in, and the products are what you get out. So this is going to be your new chemical substances that you'll see. What you'll notice is that all the atoms that we put into the reaction come back out on the product side. So we have carbon on both sides, we've got oxygen on both sides, and we've got hydrogen on both sides. What you may notice is the amount is not the same, and that's what we'll be addressing in just a little bit. Some important things for you to keep in mind when you're writing chemical equations is there's symbols that we have to use in chemistry. We use a plus sign to separate reactants and products. We use an arrow to show how the reactants turn into products, so it shows the direction of change. It'll always point from left to right. Second semester, we'll start to see these double arrows, and that means we have a reversible reaction that can go both backwards and forwards, and we'll talk more about that second semester. And then we'll see states of matter. And these are really, really important because these are going to give us an idea as a chemist about how the atoms are interacting with each other. So a small s after a substance means it's a solid. A small L means it's a liquid. A small g means it's a gas. And a small aq means it's aqueous, which means dissolved in water. So these symbols are things that we will use in chemistry, and they're always going to be found in parentheses. Sometimes what you'll see is we'll give you word equations, and we'll want you to take that from the words to the actual pieces. So for example, if I put solid aluminum with liquid bromine, I'll get the ionic compound aluminum bromide out in that process. So we would want to be able to take that using our periodic table from words into a skeleton equation, meaning it's not balanced and it's just got the main components in it. So aluminum on our periodic table is Al. Bromine, remember, is Hankelbrief, so it's Br2. So if you didn't write these elements down previously, make sure you write them down. Your diatomic elements are found in nature stuck to a buddy, and the word you can remember them by is Hankelbrief. H-O-N-C-L-B-R-I-N-F. If you see any of these words in a chemical equation, it means that it exists as a pair. So bromine means Br2, hydrogen means H2, nitrogen means N2. All of these elements do not exist individually in nature, they exist as a diatomic pair. So there's two of them together, and that has to do with the idea of wanting to be octet happy and stable. The only way these guys can be happy in nature is when they're with their buddy. So keep that in mind. You might want to write that down somewhere. So this would be our skeleton equation. Now we get AlBr3 using our charges. Aluminum is a +3 ion on our periodic table, and bromide is a -1. So in order for our compound to be chemically neutral, it would be written as AlBr3. Now what you might notice though is the amount of each atom is not the same on both sides, and this is really important because in order for us to have a balanced chemical equation, the number and type of atom must be the same on both the reactant and the product side. So in order to achieve this, we use coefficients in front of our elements and compounds to go ahead and balance out the total number of atoms, so that our reaction obeys the law of conservation of mass. Because remember, matter can't be created or destroyed, it is conserved. So that means all the elements we put into the reaction have to come out on the other side. So how I like to teach balancing is through using an atom inventory. It's just a little T-chart where R and P means reactant and product, and then you put the elements that you have. So we've got aluminum and we've got bromine. On the reactant side, we've got 1 aluminum and we've got 2 bromines. On the product side, we've got 1 aluminum and 3 bromines. So what we want to do is we want to go ahead and balance this. Now, because this number is even and this number is odd, we can go ahead and we can get them to a common factor. And the common factor between 2 and 3 is 6. So I would want to put a 2 in front of AlBr3 to make this 6 Brs and 2 Als. And I would want to put a 3 in front of my Br2 to make that a total of 6 Brs. Now, because I've got 2 aluminums on this side, I need to put a 2 in front of my aluminum over here so that it's balanced. So just like coefficients distribute in your math class, they do the same thing in chemistry. If I have a 2 in front of a compound, it means I have 2 of this whole thing. So I've got 2 aluminums and 6 bromines. The 3 means I've got 3 of this whole thing, so I've got a total of 6 bromines, and the 2 means I've got 2 of my aluminums. So my atoms are balanced, so I have a happy and balanced chemical reaction. So let's go ahead, let's try a few more. For this one, I've given you the skeleton equation, and we want to go ahead and we want to use our atom inventory to balance it. So I'm going to go ahead and write this up here. So we've got our reactants and our products. Oh, I'm going to need more space than that. Let's go ahead and remake that. Come on, that's not going to be enough space. We will put it over here. So I've got my reactants and my products. So on my reactants, I've got Na. Now, see how you've got a hydroxide group here and a hydroxide group here? If you have the same polyatomic on both sides, I like to put it in a box. Because what you can do is you can balance it as a whole polyatomic group. So I can balance my OHs, I can balance my CAs, and I can balance my BRs. So I've got 1 Na on my reactant side, I've got 1 OH on my reactant side, I've got 1 CA, and I've got 2 BRs. On my product side, I've got 1 CA, I've got 2 OHs, I've got 1 Na, and I've got 1 Br. So if we look at our inventory, the places that were not balanced are in our bromines and in our hydroxides. So I'm going to go ahead and I'm going to balance my bromines first. I've got 2 on the reactant side, so I want 2 on the product side, so I'm going to put a big 2 in front of my reaction. So now I've got 2 Brs on my product side, but I also now have 2 NAs. So I'm going to come over here to my reactant side, and I'm going to put a 2 in front of my NaOH. So I've got 2 NAs, and now I've got 2 OHs. And if I look at my inventory, I'm now balanced. I've got 2 NAs on both sides, 2 OHs on both sides, 1 CA on each side, and 2 BRs on each side. So it's just kind of a guess and check system until you get all your atoms balanced. If I give you a word equation, what we'll need to do is we'll need to actually write the equation first before we go ahead and balance it. So I've got iron 3 chloride reacting with sodium hydroxide, making iron hydroxide and dissolved sodium chloride. So we've got a couple of word clues here. So in water means that this reaction is going to be an aqueous state of matter. I'm producing solid iron hydroxide, so I know that's going to be a solid state of matter. And dissolved means that I am aqueous. So I've got my states of matter. So now we just have to make our compounds using our ion charges. This 3 tells me that iron is a 3+ ion and fluoride is a -1. So my first reactant is FeCl3, and that's going to be aqueous. I'm reacting it with sodium hydroxide that's also aqueous. I know it's a +1 ion and a -1 ion, so it's just NaOH. That's producing iron hydroxide. This is +3, this is -1, so I need 3 of my hydroxides. And that leaves me with sodium chloride, which is +1 -1. And that's also aqueous. So now I want to go ahead and I want to balance. Now, do you have to make an atom inventory if you can quickly do it in your head? Not at all. So I'm going to show you how to do this one without an atom inventory. If I look here, I've got 3 chlorines on this side and no chlorines on this side. So I'm going to go ahead and put a 3 in front of that compound. That means I have 3 NAs. I only have 1 NA over here. So I put a 3 in front of that compound. I have 3 OHs now, and look, I've got 3 OHs, so I'm balanced. So you don't have to use an atom inventory if you can do it quickly in your head. While you are starting to learn to balance, I do recommend an atom inventory in the beginning, but as you get better at balancing, you can go ahead and get rid of that. Now our last example is going to be a little bit more of a difficult one. We've got ethane gas, which I've given you the formation for, combusts with oxygen to form carbon dioxide and water vapor. So that word to form means these are going to be my products, and my reactants are going to be ethane gas and oxygen. So let's go ahead and let's write our reaction. Oops, sorry, I accidentally hit a button over there. So I've got C2H6 combusting with oxygen. Remember, oxygen is one of those Hunkebrück guys we just taught you. So we have to write it as O2 to form carbon dioxide, which is CO2, and water vapor, which is H2O. And our states of matter are going to be a gas, a gas, a gas, and a gas. So for this one, I like to do an atom inventory because I've got O's in 2 spots here. So I'm going to go ahead and do my reactants versus my products. And this is C, H, and O are my elements. I've got 2 carbons, 6 hydrogens, and 2 oxygens. Over here, I've got 1 carbon, I've got 3 oxygens, and I've got 2 hydrogens. So let's go ahead and balance this guy. Do you see how you've got O's in 2 spots on this side and only 1 O on this side? Leave your O's to last, because as I balance my C's and my H's, my O number is going to change. So let's go ahead and let's start with our C's. I've got 2 C's on the reactant side, so I'm going to put a 2 in front of here to balance those out. So I've got a total of 2 carbons now, and in this compound I have 4 oxygens. Over here I have 1 oxygen still, so 4 plus 1 gives me a total of 5 oxygens on that side. Let's go ahead and let's do our H's now. I've got 6 H's here and 2 H's here, so I'm going to put a 3 in front of that guy. So that makes my H's a total of 6, and now in this compound I've got 3 oxygens now. So 4 plus 3 gets me to 7. I've got O2 here, but I need to make it a total of 7. I can cheat this a little bit. What I can put in front of here is I can make it a little half-Z guy. So if I make this coefficient 3.5, 3.5 times 2 gets me to 7 O's, so my atoms are all balanced. But I can't really have half of an oxygen. So what I can do is I can take this entire equation and I can multiply it by 2. I call this the half-Z rule. So when you're balancing, if you get to a point where you need to put in a half atom to make it balance, go ahead and do it, and then when you get done, just multiply the whole thing by 2 to make yourself have whole number coefficients. So I don't have 1 C2H6, I have 2 C2H6. I don't have 3.5 oxygens, I have 7 oxygens. I don't have 2 carbon dioxide, I've got 4 carbon dioxide. And I don't have 3 waters, I now have 6 waters. So this would be our final answer down here. And so again, I call this guy the half-Z rule. When you get to the end, if you have to go ahead and put in a half-Z to make yourself balance, do it, and then just multiply it by 2. So balancing, the only way you can get better is through practice. So here's what I'd like you guys to try and do. I'd like you guys to try and write this reaction and balance it, and go ahead and put it in your Google form. Now I know you can't do subscripts on the Google form, so you can go ahead and just, write it like a normal. So like an H2O would look like H2O on the Google form, that's fine. So go ahead and type in the answer once you're done balancing. And then please make sure you put any questions you have, because I'm sure there are some on this. And then all we're going to do tomorrow is look at your questions and go ahead and practice some balancing. Remember, I'm always at